All right, so that's where we left off on the last video. You can see on the screen there, but there was a couple things left on the slide we didn't get to. One of them is notice where what crosses the boundary, right? And then, well, then what if I ask the question, what crosses the boundary here? And then the correct answer is, well, where is the boundary? Like what is the system? It's if I consider this gray shaded area on the slide here, the system boundary, which is what's being pointed to right here, right? It's saying, hey, here's my system boundary. If I consider that to be my system boundary, notice that's a closed system. There's no mass crossing that gray border around the system here. That's a closed system. So no mass is crossing that boundary. And it's also a cyclic system, right? It's a cyclic system. What do I mean by a cyclic system? Well, and I'm going to try to squeeze this guy down just a little bit. There he goes. So a cyclic system, and that's one of the terms we talked about in chapter 1. I said, hey, we probably won't have time to talk about this in class, but it's in your book. You should read about it. Here it is. A cycle is any system that returns to its initial state at the end of the process, right? So that means that if I plot this out on a pressure volume diagram, a cycle is any process that gets the system back from its initial state, from at the final state all the way back around to its initial state. The final and the initial state are the same. So this heat engine that I've drawn here is a cyclic system, meaning that coming into the turbine is the same as what's coming out of the boiler. Right? It's returning back to that initial state once the entire process is done. So if the process is a closed system and it's a cycle, meaning it returns back to its initial state, so if it's a cycle, that means the right-hand side of the first law, the change in the energy of the system goes to zero, right? And actually what we're saying there is this right-hand side, delta E system, we're saying that delta E system, which is just the final internal energy minus the initial internal energy, well, those are both U1 minus U1. U1 minus U1 means it's just equal to zero. So the only thing that I'm left with then is all of these other terms. I've got heat coming in up here. I've got work going in at the pump. I've got work going out here at the turbine, and I've got heat going out at the condenser. And if I add up all four of those terms around the cycle, that change is zero. This right-hand side for a cycle is going to go to zero. So what that means is that the net work out is for this cycle. The net work out, which is the difference between work out and work in. Well, notice if these four terms add up to be zero, that means if I move work out and work in to the other side of the equation, that means work out minus work in equals Q in minus Q out. So the net work out, the difference between work out and work in, is equal to the difference between heat in and heat out. Now, remember our good friend efficiency that we talked about in chapter 2, and I said, I wish our text would talk about efficiency more throughout the text, but here we are. Well, now we need to talk a little bit about efficiency. So efficiency, the efficiency, which your text loves this idea of output over input, and I've always tried to talk about, okay, think about what you want or what you expect to be the smaller quantity divided by what you expect to be the larger quantity. Well, if you think about what you want divided by what you have to do to get there, in this case, the efficiency for a thermal engine or a heat engine is going to be what you want. That is the net work out. That's what you're going to sell or what you're going to use to make profits, so to speak. Divide that by the heat in, right? And since we've already set up here that the net work out is equal to Qin minus Q out. I'm going to stop share here so we can see this. Right? Since the net work out is equal to Qin minus Q out, and the efficiency is the net work out divided by the heat in. Well, if I plug this in for the net work out, that means this is Qin minus Q out divided by Qn. That equals the efficiency. And if that's true, I can split this numerator into two different fractions. Well, I've got Qn over Qn. Those are non-zero, right? Qn over Qn minus Q out over Qn. Since these are both, neither of those are going to be zero, this is going to be 1 minus Q out over Qn. The efficiency can be found as either the ratio of what you want, our output, the net work out, divided by what you have to put in, Qn, or it can also be found for a heat engine as 1 minus Q out over Qn. Okay. Now, with that in mind, then, here are here's a very simple example with very simple numbers, so we don't necessarily have to bust out a calculator to prove this to ourselves. If I've got a furnace kicking out 100 megajoules into our heat engine and 55 of those megajoules are coming out as work out, that means the remaining 45 kilojoules, or sorry, 45 megajoules are going to have to be rejected to some sort of a sink, some sort of like an atmosphere. So, right, again, the net work out has to equal Qn minus Q out. Okay. Now, what they are showing you here, the other thing to mention is this text is going to use subscripts of Q and L to refer to the high temperature and the low temperature. Right. So I did that on my diagram up here just out of habit. TH is up here, TL is down here, meaning this is going to be QH, the heat coming from the high temperature or the heat at the high temperature reservoir, and QL, the heat at the low temperature reservoir, right? And so what that means then is that, so a lot of times your text is going to use, instead of in and out, it's going to use H and L for a heat engine. That means that the net work out is going to equal QH minus QL. Again, instead of QN, we're going to call that QH, the heat from the high temperature source. And instead of Q out, we're going to call that QL. All right. If that's the case, then we're going to say that the efficiency is going to be this net work out divided by QH, or 1 minus QL over QH. Which is what's there on the slide, right? But these are the fundamental expressions. This is a simplified version of the first law, and this is our efficiency equation. So two major equations we're going to use anytime we encounter a heat engine in this chapter. Okay. Now, remember our good friend Clausius told us that it is impossible to construct a device operating in a cycle and produces no effect other than transferring heat from a low temperature body to a high temperature body. That can't be the only thing this device does. Doesn't mean it can't happen. In fact, we experience this all the time. It's summertime here in the middle of the country. We're very used to air conditioners and refrigerators. These are devices that actually move heat from a high temperature body, or move heat from a low temperature body to a high temperature body. But that's not the only thing it does. The main thing that it does on top of that is it's going to require a work input. Right. So a refrigerator is a device that requires work input, and using that work, it's basically going to pump heat or move heat from a low temperature medium to a higher temperature medium. Now, in a refrigeration cycle, the working fluid is also going to be called a refrigerant. So standard refrigerants are substances that undergo pressure temperature phase changes at very convenient pressure temperature combinations for us. So your R134A that we work with in the tables is a type of refrigerant that's identified as very good for operating in refrigeration cycles that we would normally use. Okay. But that's what refrigerant refers to, is that's the working fluid that moves energy from one part of a refrigerator to another. All right, so I'm going to expand this out here and I'll draw a refrigerator with you so you can draw it in your notes. How am I for time? Oh, good. We got plenty of time on this one. Okay, so if we were to draw a refrigerator, again, you can see it there, but I'm going to draw it with you so you can draw it in your notes. So a refrigerator is fed by a compressor. So I'm going to draw the compressor first. And my preference is to draw the turbo version of a compressor, kind of the opposite of a turbine. You can see this particular text here uses a piston cylinder type of compressor with a mass in and a mass out. I don't particularly care for that. I like to keep a piston cylinder as a closed system, but I understand why they're doing it. And if you look at how most small compressors are manufactured, they are often kind of like a piston cylinder, but you can also have them in this turbo configuration, where it's basically a rotating shaft with some blades inside. But that compressor, the goal of a compressor in a refrigeration cycle, I always say the goal is to get the refrigerant screaming hot. The goal of a compressor is to get the refrigerant so hot that when I run it through the condenser coils, which is just a heat exchanger, when I run it through the condenser, that refrigerant is actually hotter than the high temperature sink that we're trying to dump this heat into. This is QH going into a high temperature sink. So this would be like your outside air for your air conditioner system. Your if it's your refrigerator in your kitchen, for example, it's this QH. This is the heat you feel coming off the back or the bottom of your refrigerator going into the kitchen space. This is QH that you're feeling there. The coils, the little tubes that you see, or the outside unit, the outside part of your air conditioner, that's your condenser. That's just a heat exchanger that the refrigerant is running through, and air is being pushed through those condenser coils to carry heat out of the refrigerator into the outside environment. So again, the goal of the compressor is to get high pressure and high temperature to squeeze and compress this refrigerant so much that it gets so hot it will actually now lose heat to the outside environment. And then from there, well, let's start on the bottom. So before I say that, so if we look at the bottom part of the refrigeration cycle, so what feeds the compressor, on the bottom of the refrigeration cycle, you're going to have another heat exchanger we call the evaporator. The evaporator is where we remove heat from a low temperature body, a low temperature source. So this is the space we're trying to refrigerate or to cool. So we have inside of a house or inside of the refrigerator or freezer unit where we're trying to remove heat from the food or whatever we put inside the refrigerator. And this is the QL. This is the heat at the low temperature being absorbed from the food inside or the air inside a house. It's going to flow through another heat exchanger. We're going to blow air from this into a heat exchanger and then push cold air back out into this area to kind of cool it down. And all the while, it's basically heating up refrigerant that's flowing through here. And it's flowing through what we call evaporator coils. And what happens is we put enough energy into the refrigerant that it becomes a very low pressure vapor that we can then compress and get it up to a high pressure, high temperature vapor, and the cycle continues. Now, over here is kind of a bit of a magic. And I say that and I chuckle because I've actually had a former student of mine he's a registered professional engineer. He works for an architectural firm, but He's a mechanical engineer, and his job is he actually sizes the large scale air conditioning HVAC units for like school buildings or other large facilities that his architectural firm goes out and bids contracts on. And he actually came and talked to my intro class and was introducing him to the refrigeration cycle. And he actually, this is a working professional engineer out in the field, and he says, here's the magic part, the expansion valve, because it kind of is magic. The best way I know to describe the expansion valve, we talked about the compressed can of aerosol, like the computer cleaner, where if you hold that thing open for a long period of time, how it gets cold. This is kind of the same basic principle. On this side, I've got high pressure. This is like inside the aerosol can. And if I hold it open for a long period of time, the pressure drops. And as the pressure drops, the temperature drops. And so this is kind of the same thing as that, except it's a continuous flow situation. So you get this high pressure material gets squeezed down to a choke point, and then you allow it to expand on the other side. And as it expands, it speeds up, and the pressure and the temperature end up dropping. So you go from a high pressure, high temperature to a low pressure, low temperature on the other side. And a lot of times it ends up kind of dropping down to a saturated mix or maybe even a liquid. But it's similar to, again, to kind of the idea of if you hold open an aerosol can for a long enough period of time, as it expands out from the low pressure inside the aerosol can to, or the high pressure inside the aerosol can to a lower pressure after the expansion process, that it gets really cold. It drops. That pressure drops, so the temperature drops at the same time. That's the basic premise. In the simplest terms I can put it, that's essentially what's going on inside this expansion valve. No moving parts, very low tech, very simple way of getting to go from a high pressure, medium temperature to a low pressure, low temperature. Now this refrigerant is at such a low temperature that when I expose it to the low temperature or the low temperature medium that I'm trying to further cool down, the refrigerant is actually colder than this low temperature medium. And so it will actually absorb now heat as it runs through this evaporator from that low temperature medium. And we can actually cool the inside space, which is the goal of a refrigerator. All right, I'm going to stop there and we'll look at equations on the next little bit here.